Now that we discussed what machine learning is and what the major categories of machine learning are, let us now return to supervised learning. Remember, that's the biggest category of machine learning, supervised learning, and talk a little bit about the notation, terminology, and broader concepts of supervised learning. So supervised learning, the main workflow looks like this. Recall supervised learning, we said there are two categories or subcategories, regression and classification. And here I'm referring to either a regression or classification, could be both. So that's the main workflow where we have a training data set. And in the training data set, there are the so-called features. Here I just wrote training data, but you can also say features or observations. And then we also have the target information, the labels. For example, class labels in the case of classification. So we provide this training data set then to the machine learning algorithm. And there are many, many different types of machine learning algorithms, which we will see later in this course. And the algorithm will turn the data into a predictive model. So the model is learned by the algorithm from the training data, and it can then be used to make predictions on new data. So for example, if I have new data which has the same form as my training data, so the same features, then I can use my model that has been trained on the training data to make new predictions. So that's the main workflow. Later we will return to this workflow figure and look at more details, but just for the big picture, that's how usually a supervised learning workflow works. Okay, let's now talk a little bit more about the more formal aspects of supervised learning, the notation. So here I have a training data set. Let's call that D. And this training data set consists of n training examples. So I have n, so 1 to n training examples. And each training example, so that is one training example, consists of a feature vector and a label, so the target information. And I'm using the superscript I here to denote the ith training point, so the position or the data point or data pair, the pair of feature vector and label in the training set. Later we will use a subscript for something else, which is why we use the superscript here. So instead of writing it like this, I'm writing it with this superscript, and why it will become clear later, because we will use the subscript for something else. Okay, so that is the training set, and there has to be something that generated the pairs here. So there was some function that assigned the label to the particular feature, and this is usually an unknown function. So usually we have a data set, there could be a function in a way, there could be a human labeling emails as spam and non-spam. So in that case, the human would be the function providing these labels. But again, if you would ask a human how the human would assign spam and non-spam, this is kind of a function that you can usually not describe in words. You just recognize, okay, this is spam and this is not spam. So there's usually some underlying unknown function or natural phenomenon that assigns these labels to the features. And the goal then, so let's call this function f of x, that assigns the labels. And the goal then in machine learning is to learn a model that approximates this function, ideally to learn this exact function. But this is usually tricky, so because there's an arbitrary number of possible functions, so machine learning usually tries to find a function that provides also a similar mapping between x and y as this unknown function. And we call that in machine learning traditionally the hypothesis. So this is, you can also think of it as the machine learning model. The hypothesis or model would be a function learned by the machine learning algorithm that makes the predictions. I call them here y hat. So this is a prediction of the class label given a feature vector, and y would be the true label. And then when we evaluate our model, we usually have a separate data set, but we will discuss that in more detail later. But we would basically compare how close the predictions are in the case of regression. And in the case of classification, we would check whether the true label is the same as the predicted label. So maybe at this point you can pause the video and think about, in the case of classification, if I have a feature vector here, which is a vector usually consisting of real numbers. So this would be my feature vector. And here I have 1, 2 for regression. So if I give it the feature vector, and I mentioned this already multiple times when I was talking about this slide, what should go here on the right-hand side? So the hypothesis takes in this x, and what does it output? So just a maybe way to double check that you followed the concepts on the slide. Maybe pause the video now, and I will resume in a few seconds now. Okay, so here in this case, the classification algorithm would take in a feature vector, x, and the output would be the class label. So this would be a set of possible values. It's right as in set notation. And usually in machine learning, we use integer numbers, for example, 0 and 1 for binary classification problem. If we have 3 possible classes, we would have 3 labels. However, it is kind of arbitrary. We usually use integers because it's easier to program in a computer, but we can also use some arbitrary letters for denoting the class labels, ABZ or ABD, ABC, whatever you like, really. So there is also no order in these labels in classification. There's a special type called ordinal regression or ordinal classification, which is a little bit out of the scope of this lecture. So in regular classification, there is no ordering in these labels. And if you see something like 0, 1, 2, it can sometimes falsely give the impression that there's an order in the labels. But in classification, these are nominal and not ordinal classes. So this is nominal and not ordered. So there's no ordering relationship. You can't say that 0 is smaller than 1 and 1 is smaller than 2 in terms of classes. Any case, that's going on a tangent here. So going back to what should go here, in a regression example, that would be the continuous class label. So y would be a continuous label. So we would usually have a real number here as output. Okay. So let's briefly talk about feature vectors. In the previous slide, you maybe have noticed that I used a bold version for x. So for the ith training example, I had the bold x for referring to it as a feature vector, and I used a non-bold version for the label. That is because the label was a single data point or a single value, and x here was a vector. So this is a vector, and this was y was a single value or scalar. For scalars, I don't use bold font. For vectors, I use bold font. If I do my handwriting, it's kind of tedious to make this bold font, so I will try in this course to use a X with an arrow above to refer to a vector. So a vector can consist of many different features. So a feature vector is just a list, if you will, a vector or a list of feature values. So here in this case, I have m feature values for this feature vector. So if this is the ith training example, I would put the I above here as a superscript. And that is also why I'm using this square bracket notation for the training index, so the data index of the training set, whereas the subscript here, that's the index for the feature in the feature vector. Now each feature vector corresponds to one training example. However, in practice, the training dataset consists of multiple training examples. So usually we have n training examples in the training set. And in order to denote that, we can use a matrix where each row in the matrix corresponds to a feature vector. So I'm using the transpose here to transpose each feature vector. So the transposed version, this would be then a feature vector x1, x2, x3, xm. And each row here would be one training example. Unfortunately, because we have the transpose up here, it's kind of a little bit awkward to put the index up there also as a superscript, but this would be 1, 2, and n. So instead of using these subscripts here, maybe a little bit more clear in that way. And there's actually a particular name for this matrix where we have multiple training examples as rows. So it's the first training example, the second, and the nth training example. And again, this is the first feature. Actually, first feature would be here. First feature, second feature, and mth feature. So if I have this representation, there's a particular name for this, and I think you've probably seen that in other statistics courses before. And that would be an excellent point now to pause the video briefly and brainstorm how this particular representation is called, just to maybe make the connection for yourself to previous courses. So I have some blank letters here. There are 2 words to denote this kind of representation. So pause the video now and think a little bit about how this representation is called. Okay, so that is, if you don't know it, I think it's probably hard to guess. It's a little bit of an awkward name, but it's called design matrix. So that's the design matrix notation. And we will use that design matrix usually to refer to the training set or in general to data sets in machine learning. So that is a very common representation and something you should ideally be familiar with. Going a little bit further, so if you found this representation of the design matrix a little bit confusing, there's also another way to write this out. And here on the right hand side, I'm just expanding it. So again, that was what I was showing you before. So this is one feature vector of the first training example. And here I'm taking this one, transpose it to a row vector. So this is the row vector now, and which would be corresponding to this one here. And here I put the index 1 because it's the first training example, and there are 1 to m features. And in that case, of course, this is a design matrix. And this is exactly the same design matrix, just written more explicitly. Okay, this is just some of the notation. It's just something to keep in mind. It will become very familiar to you over the course of this course, because you will be also writing this in code later on in Python and scikit-learn using matrices. So in that way, this mathematical notation will be exactly the same format that you will be using in code. This was a little bit too abstract. Let me show you these concepts in the context of a real dataset example. So this is the IRIS dataset, which is a dataset collected originally by Edgar Anderson and published in a paper by Ronald Fisher, which is why it's also sometimes called the Fisher's IRIS dataset. And this IRIS dataset consists of flower measurements. So there are these iris flowers, and there are different measurements about the petal and sepal leaves. So I'm not confident that I got it correctly, but I think these are the petals, and these kind of leaves are the sepals. And I think I was incorrect. So I think this is the petal, and this is a sepal. And for each flower, there is a measurement about concerning the width and the height Same for the sepal, the width and the height. And these 4 measurements, so we have 2 measurements here, 2 measurements here. These measurements are our features, so 2 and 2, that's 4. So we have 4 measurements. These are our features. So here, this part, let's call them the features. And then we have a label information. So the goal in this dataset is to predict a flower species based on these measurements. And there are 3 different kinds of flowers, or iris flowers. So these are subspecies of iris flowers. There's a Setosa class, Versicolor, and Virginica. So 3 different classes, or 3 possible classes. So these are our labels in this column here. Then we have 150 of these measurements and class labels. So we have in the training set, so our training examples from 1 to 150. So usually in this class we will try to stick to the same notation for basic things like number of features and number of examples. So n would be the number of training examples, that is 150. And we have m equals 4 features. So 1, 2, 3, 4. And that is an iris, or the popular iris dataset that we will be working with throughout the semester when we look at different machine learning algorithms. Of course, we will also talk about different datasets, but I think it's it's kind of overused, this data set in machine learning, but I think it's still a good data set to explain basic concepts because it's not very complicated and it helps us focusing on the method and not getting distracted by what different data features mean and stuff like that, because I think this is very intuitive. We have flower measurements and we want to predict the flower species. After the previous slide, you probably know there are 2 types of vectors. There is the vector containing the input features, and we can also use the vector for representing the class labels in the training set. So that was the rightmost column in the picture in the last slide. So if we have multiple training examples, 1 to n, we can also use the vector y to represent the labels. So we would call that the label vector, whereas this is our feature vector. However, don't confuse those two, because this is over the number of features and this is over the number of training examples. So if we want to represent all the feature vectors of a training example, we would have to use the matrix, the design matrix, where we have 1 feature vector as a row vector in each row, so up to n of them. Okay, that was what I wanted to cover about the notation. We will see some more notation later in this course, but this is basically the basic dataset representation that we will be using most of the time. So for your personal reference, I created here an overview slide containing the different terms we heard about so far. So we have the term training example to refer to a particular data point in the training set. For example, a single flower in the iris dataset. We have a feature, the term feature, which refers to a measurement for this particular flower. For example, the sepal length. We have the targets, where a target would be the class label. In the case of the iris flower example, that would be, for example, Versicolor. And then we have the output or prediction, which would be the predicted class. So that could be any of the 3, but ideally our model would predict the same as the true target, for example, Versicolor also in this case. There are many words on this slide. I don't want to read them all out. It's probably a good idea though to look over this, because I was summarizing all the different words for the same concept that came to my mind. Because sometimes, depending whether you read computer science papers, statistics papers, electrical engineering papers, researchers in machine learning, they use different words to refer to the same thing. And here I was just trying to list all of them that I've heard before. So it's very common to say training example, but sometimes you can also say, or some people say, observation, training record, training instance, or even training sample. This is very common in statistics. However, I don't want to use the term training sample here because it can be confusing, because sometimes we refer to sample as a collection of data points, and some papers they use the word training sample to refer to a single data point, which is then I think confusing. So if you just say training sample, it's not clear whether you mean one data point or multiple data points. So we will try to stick to the common terminology in machine learning using training example to refer to one data point in the training set. Then the feature, in statistics we also sometimes say predictor or covariate, sometimes also variable, input, or attribute. So there are many different words again for the same thing. We'll try to use the term feature because that's most common in machine learning. Targets, for that we also have different words: outcome, output, ground truth, response variable, dependent variable, and in the case of classification, class label. And then lastly the output and prediction. So that is, we can use the same terminology as here, like output, but with output we usually mean what's predicted by the model. So this is the prediction by the model, and the target is usually the actual target. We also often say ground truth, the real one, the real label that we want to predict. So we want to use the model to predict this value with the model, and that is the output of the model is called the output or prediction then. Okay. There's one more term I want to cover here. That's the hypothesis space. We will encounter the word hypothesis space multiple times in this course, which is why I briefly want to highlight what I mean by that. So a hypothesis, I mentioned that before, this is kind of synonymous to model or classifier. It's just a, I would say, more classic way of referring to a model. And what I want to show here is that there are multiple different hypotheses that we can learn. Every function that can be learned can be represented in this hypothesis space. So if there's some function that maps the features to the labels, the entire hypothesis space consists of all such functions that map x to y. And using machine learning, we want to find the one that approximates the true function best. Ideally, we want to find the true function, but there are so many different possibilities, so it's hard to find this. So sometimes we just approximate the label generating function. So let's just assume there's this whole space of possible hypotheses that we can search. So these are all the possible functions. And then when we use a machine learning algorithm, we usually only sample or evaluate a subset of this. So you can say this is our subset. And in this case, let's call these, it's a machine learning learning algorithm category. So for example, this could be all the tree-based algorithms. So there are multiple tree-based algorithms. There's a CART decision tree. There's ID3 decision tree. There are random forests. There are many different types of tree-based algorithms. And if we consider all the possible tree-based algorithms, we would maybe have access to this space of the hypothesis space. So there are certain functions that we can't find using tree-based algorithms, so we only have access to a subset. Then, let's say we pick a particular case, particular tree-based algorithm. Let's just say we focus on this CART decision tree. And we will talk about decision trees in way more detail later in this course. I'm just trying to give you an example of what I mean by hypothesis space here. So picking one particular type of algorithm from the family of tree-based algorithms, what I have is I again have a subset of possible hypotheses or models that I can sample. So this is now here a much smaller set. And then if I have a training set, a particular training set, and there are also certain options I can set in the algorithm, like how deep the tree should be maximally, or how what kind of function I use for information gain. We will talk more about information gain later. Then I come up with a very particular model fit to my data set, and this particular model is then my hypothesis. So what I'm just saying is, if we want to sample the whole hypothesis space, we have to consider every possible function, which is usually not feasible, which is why we use machine learning to approximate this, or to approximately find a function in this space. And depending on whether we use certain types of algorithms, we have access to certain areas in this hypothesis space. For example, if I would use logistic regression, I would have maybe only access to this part of the hypothesis space. So let's maybe put it here. So different algorithms sample the hypothesis space in a different region. But it doesn't mean, so the true function, maybe none of the algorithms is able to sample it. So usually we are already happy if we can approximate the true function. Okay, there was a long monologue here. Let us just move on to the next slide. Like I explained in the previous slide, there are different types of machine learning algorithms that sample different subspaces in the hypothesis space. So here are the major families of machine learning algorithms. For example, generalized linear models. One example would be logistic regression. And then we have support vector machines. Then we can have a linear support vector machine, and there's something called a radius basis function kernel machine. Let's call this RBF kernel SVM. We have artificial neural networks like the multi-layer perceptrons, or there are also recurrent neural networks and convolutional neural networks and so forth. We have tree or rule-based models, for example, decision trees. Then we have graphical models. One example would be Bayesian networks. Then we have ensemble methods. One case would be the random forest. We have instance-based learners, which, for example, could be a k-nearest neighbor algorithm. So there are many different types of families. Here I'm trying to list the main ones. And in this course, we will cover most of them. So we won't talk about logistic regression in this course. And we will not talk about neural networks, because there will be a separate course I will be teaching in spring, which is STAT 453. And this is the introduction to deep learning. And in this course, I will talk about deep learning, multi-layer perceptrons, convolutional neural networks, recurrent neural networks. And in the introductory parts, I will also cover logistic regression, because you can think of logistic regression as a special case of a single layer artificial neural network. So in that case, I don't want to cover the topic in both classes, because I know many students take both classes, the machine learning class and the deep learning class. So these two topics are covered in the STAT 453 class. We will not cover support vector machines here in this class either, but we will cover all of these methods. And there are plenty. And in addition to these machine learning algorithms, I will also talk a lot about other concepts related to machine learning, like machine learning model evaluation and so forth, which are very important. And once you understand the basic concept of machine learning, you can easily learn about additional algorithms later. So here in this course, we are trying to lay the groundwork, introduce some machine learning algorithms, of course not all of them because there are so many of them, but after this course you should be able to do more reading and learn about additional algorithms that we don't have time to cover in this course. So in the next video we will then talk about how we approach a machine learning application.